Now let's begin our venture on the Bayesian-based models. And Bayesian means that somehow our models would be able to incorporate estimates of probabilities. So these are a category of models that are inspired by some form of representation of a belief of an aspect of the data. And that belief is updated conforming to the data that is available. So let's have an overall idea of more specifically what we mean by a canonical Bayesian classifier. So before we had introduced one of the examples as what you see in the screen. So in this example here, I would have three classes. Out of these three possible classes, I would be generating a score. So each class would be associated with a score. And then essentially I would have one regression function being used to generate each of those scores. And based on the outscores that I have, we could use a simple rule by just identifying the one class that would have the highest score among all the scores that we have. After we identify that, that would be our classification. So that would be the rule, the decision rule that would be used to output a class. Now, in the case of a Bayesian classifier, a few small changes would need to take place. So first thing is our scores would be thought of as now as probabilities of class probabilities. So now we are no longer just thinking about scores, but we are thinking about each class score as the probability of that given input belong to that class. And we name that specific probability, the probability of the class given the input, as the posterior probability. So essentially what we are estimating in this case is the posterior probability. Because these are now probabilities, we have a few things that we can also take advantage of, right? So the first thing is every probability varies from 0 to 1 necessarily. The second property is that the sum of these of these scores, of these probabilities, would be equals to 1. So no matter how many classes, no matter how many categories you have as the possible outputs of your classifier, when I sum up all these, all the scores, all the probabilities, the posterior probabilities of the class, I would necessarily be summing up to 1. And this is actually a rule that applies to any probability distribution that you have. So as long as if you are talking about a discrete series of possible outcomes, so then you just need to enumerate those, and then you can sum up to 1. If this is a continuous probability function, then you need to integrate that, but that would still integrate to 1. Now let's introduce a very common function that is the softmax function that is used as a very popular way to normalize our scores. So if you are using a function that is a continuous function from a given range, that might even be the range of -infinity to +infinity, you need to somehow shape or transform that output of that function to a range that is suitable to a probability distribution. And the way that, as I mentioned, we very popularly do that is just by applying the softmax function. So the softmax function is the most popular way to estimate our probability, in this case, the posterior probability, because we want to estimate the class of a given input. So given that you know the input, so the class probability is conditioned on the input, you want to estimate what the probability of that class belonging to to that input, or the other way around, actually, right? So the input belonging to that class. So the formula for the softmax is actually quite simple. It's just the E constant to the power of the output normalized or divided by the sum of the E to the power of every other output that we have. So essentially, you are iterating over all, in the denominator, you are iterating over all the outputs. So every class output that you have. So for instance, if you have 3 different classes, this essentially is just a summation of three powers of those numbers. And in the numerator, you would have the E to the power of the output of that specific class. So if you do that, you would have the 2 nice properties that we want, which is have the number, the probability sitting between 0 and 1, and also having the sum of all the probabilities as equals to 1. So now let's talk about the main probability functions that we would be using. So I have mentioned already about the posterior, and the posterior, as we said, is essentially the probability function that would be used to estimate the class that a given input would belong to. We represent that usually following this terminology. So we put P of C, or sometimes we put Y hat to represent the prediction, given that you have access to a specific input. So it's conditioned on the input. The second kind of probability that we would be using would be the prior probability. So the prior probability is a probability that represents the belief of the likelihood of a given class before you observe anything on the data, right? So usually this represents the prior belief that we have, but there's a very easy way that I can actually estimate my prior, which is just looking at the ratio of samples that belongs to a given class. So imagine that you have your training data, and your training data has 100 samples, and you have 3 classes. So if in your training data, 20% of the samples belong to class 0, and 30% belongs to class 1, and 50% belongs to class 2, so then essentially your priors would be precisely those numbers, would be 0.2 and 0.3 and 0.5. So that's just a very easy and very common way to estimate the prior probabilities. So the next kind of probability function that we would be using would be the probability density, or the likelihood. So the likelihood now represents our belief in the likelihood of your input with respect or condition on the class. So this is in a way the opposite of the idea of the posterior, and we will visit in a bit why it is interesting that we estimate that probability. But one way to think about that likelihood probability is essentially a way to describe how your data is distributed, for given that you know, or given that you're coming from a specific class, because it's conditioned on the class. So you would end up with one function for each of the classes that you have, essentially. So imagine again that you have 3 classes. If you are calculating the likelihoods, you would need to calculate a likelihood function for each class that we would have. Now that we have mentioned the main kinds of probability functions that we would be working with, we can introduce the Bayes rule, which is just the equation that you see here in the bottom of the slide. So the Bayes rule essentially is a way for us to relate those different probability functions, right? So in the left-hand side here, you see the posterior probability, and you see that we can calculate the posterior probability by multiplying the likelihood function and the prior, and then dividing by a function that I did not mention, but it's called the marginal. So the marginal is just the function of the input, not conditioned on anything. The reason why I skipped completely the description of the marginal, the p of x that you see here in the denominator, is because most of the time you actually don't even need to account for that probability function. And the reason for that is because the probability of the input is essentially the same no matter what class you have, no matter what condition you have. So it's not really varying as you calculate the probabilities for the different classes. Essentially, you would have the same denominator every time that you estimate your posterior. Because we want to compare those posteriors of the different classes, and we want to obviously identify which one is the highest probability one, so which class would be associated with the highest posterior probability, we are essentially just comparing posterior probabilities or posterior probability functions. If we are just comparing those different posterior probability functions, and all these functions has the same denominator, so then I can just ignore completely that denominator. And that's the reason why we usually don't even calculate or estimate that marginal function. So then essentially, the way that I would typically estimate my posterior would be just directly using the likelihood multiplied by the prior. That's it. So you just ignore that denominator part, because most likely what's going to be done is just identify the posterior probability that would be the highest one. So here in this plot, we see some bell-shaped curves here. You see 4 distinct shapes or 4 distinct curves as part of a surface here. And you see in the bottom a projection. So this projection essentially is being identified by a couple of points, and you see these lines here as well. So let's identify what these things mean, right? So the points themselves are just the inputs from your input space, because here we have a 3-dimensional space. One of the dimensions, the one in the vertical, would actually be the scoring dimension. In this case, because we have Bayesian models, so then we would be working with probabilities. So our scores are probabilities, and that's what that axis, that vertical axis here, are representing. So in other words, if you see an apex of one of those bell curves here that is higher than the other ones, this means that this is a curve of the highest probability function. In that case, in this graph here, these bell-shaped curves here are representing our posteriors, but this could very well be representing likelihoods as well. So we will talk a little bit more about how to interpret the likelihood versus the posterior by looking at these sort of plots. But now let's talk about this region here in the bottom. So my region here in the bottom are essentially the space that are comprised of my input features. So my 2 axes here, the axes that define this plane in the bottom, they are essentially defining all my input space. So because here we have our input space, then in an input space, you can identify the decision boundaries that is determined by a model, right? Because I can identify decision boundaries. So you can imagine already that these curves here that you see my cursor hover over are essentially my decision boundaries. So compared to the decision boundaries that we saw before, there's a difference, because now we are no longer identifying the points in my input space that would have the score equals to 0.5. The way that we would actually be identifying our decision boundaries would be when we have 2 or more curves. So each of those 4 curves that I have here would be intersecting or overlapping each other. when you have the same score being given by 2 or more of those curves. So then this represents a point that is in a decision boundary, because that's essentially, again, the definition of what a decision boundary is, right? That's a point that you have at least 2 classes that are equally likely to happen in that region or in that point in our space, in our input space. And finally, these sort of ellipses or ellipsoids that you see here, these are representing the area. So these are typically referred to as topological curves, and this is just representing a region where the standard deviation or the covariance of the distribution is the same. So this essentially is a way for us to have an intuitive understanding of the overall shape of our probability distributions that would be generating those curves. This is essentially just explaining what I have previously said. The z-axis or the vertical axis is the scoring axis, and that's what you see. That's where you see the posterior being estimated, and here in the bottom is essentially the projection that you have from that, or equivalently, these would be our input space. So an important observation here is that even though here we are limiting the range that we can see from that plot, these bell curves here, or these surfaces, are infinite. So the range that you would actually have that curve would be from negative infinity to positive infinity. All that we have mentioned before. So as I mentioned, the way that we have that posterior probability estimated is usually by just ignoring the denominator that we would have in our Bayes rule equation. So then you can just calculate the likelihood, in this case, the P of X given class I, and then estimate the prior, which is the probability of the class I, not conditioned on anything. Then you, after you estimate those two things, you can just multiply and you would have a number that is the estimate of your posterior. That estimate would be not normalized because you did not divide it by the denominator. But as we said before, this does not matter because I am just comparing those different posterior functions, posterior distributions. So here in this slide, you see the decision boundary that would be generated by a Bayesian model using Gaussian likelihoods. We'll get to what these sort of likelihoods are in a bit, or how they are defined in a bit. An interesting thing that we can comment on a property that is seen on many Bayesian models is that many models are what we call generative models. So what is a generative model? A generative model is essentially a model that is capable of generating inputs. So you can think of it as a function that is capable of generating samples that represents inputs from your feasible input space. So it's not just the regular input space, but input space of the phenomena that we are here modeling. And because these are generative models, if I go the other way around, if I actually generate my data completely by using a Bayesian model or a generative model more generally, what happens is that now in this case, I would be able to perfectly estimate or recover the original decision boundaries of that distribution that had generated those inputs. So now let's move on to talk a little bit about mathematical preliminaries. We will be talking about the Gaussian distribution, and because we want to talk about the Gaussian distribution, we need to talk a little bit about vectors and means and variances and covariances and standard deviation and covariances matrices. So let's get going. So the first thing that we want to talk about are what vectors are. So most likely you already have a proper understanding of that. So a vector is essentially an object, a mathematical object that is defined based on the number of dimensions that you have. So if you have an input space that has, let's say, 20 dimensions, then a point that lives in that space can be representing equally a vector. So there's actually no distinction between a point that lives in a coordinate system determined by the sum of the dimensions that you have in your input space and a vector, right? So the vector, the idea of the vector is just a mathematical object that goes from the origin to that specific point in space. And that point in space is essentially the numbers that would identify the coordinates of that vector. So in the examples that we are seeing so far, we are using input spaces that only has 2 dimensions. So essentially you can have a vector determining each of those points or each of those vectors themselves by just choosing 2 coordinates in that input space. So a vector has 2 main properties. One, the direction. So essentially the tilting of that vector with respect to the usually the origin, but this can actually be applied to other vectors as well. And the magnitude, which is an idea of a length of that vector. And again, we usually refer to these vectors as measurements that comes from the origin. So the length essentially is measuring the distance from the point that is being referenced by that vector, by those coordinates, and the origin of my coordinate system. The way that I would calculate that magnitude is actually something that you already know, is just by using the Pythagorean theorem. So this is just taking the square root of the squares of the sums of all the features or all the coordinates that I have. And finally, if I want to work with a normalized version of my vector, a typical normalization that we would be using would be to just set the length of the vector to 1. So if you have a set of vectors, what you would be doing is essentially transforming all the vectors that are part of that set to a unit vector or a vector that has the length of 1. As you can imagine, there's a very simple way that you can do that, which is just by calculating the lengths of those vectors, and then you just divide the length of the vector by its length. So that would essentially transform any vector to a vector with a fixed length. So in this case, the length of 1. So the mean vector is a vector that is essentially storing mean values. So for each feature or for each dimension that you have in your input space, you can check, given the samples, the entries that you have in the data, you can check what the mean value would be for each of those features. If you do that for all the features, you end up with a vector of means. So that's what we refer to as the mean vector. So here you have an example given 3 vectors. So if you calculate for these vectors, for each of those, if you fix each feature, so for instance, the first feature, if you sum them up and then you divide by the number of vectors, you would end up with the mean of each of the features that we have. So you see here in the bottom. And if you have all that set as a single vector, that is your mean vector. Now let's talk about the covariance matrix. So the covariance matrix is an idea that generalizes the idea of standard deviation and variance. So this is essentially a matrix that stores not only the standard deviations that you would see in your data, but also all the covariances. So the idea of covariance is the variance, the average square difference between pairs of features. So the covariances would exist essentially for every pair of feature that we have in our sample data. So in each of our samples, and let's see some examples of that. The equation to have the each covariance or each variance calculated is what you see here. So if I want to calculate a variance, this means that you are not really considering a pair of features, but actually one single feature. So then that's the equation that you would be using, and represents the number of samples that you have. And this is just summing over all the samples. So in this case, n samples that you have. This x hat I is just the mean that you have for that specific feature. And then you are essentially just calculating the difference from that one sample to the mean, and then squaring that value, and finally summing over those measurements for every sample, for every entry that you have. So the same idea would be applied when you want to calculate the covariance, but now because a covariance is a measure that is being done between two features I and j. So again, you would go over all the samples. So the summation here is going over all the samples and represents the number of samples that you have. And you are summing over this operation here. So here we are calculating the difference from one feature from the mean of that feature. And then we are multiplying that by another difference for another feature, now feature j. So the difference from feature j from the mean of that feature. So you multiply those two values and then sum up that for all the samples that you have, and you would end up finally with your covariance between I and j. So this is just explaining everything that I have mentioned already. So the way that the covariance matrix would look like for a 2x2 covariance matrix would be what you see here in the center of the slide. So the main diagonal of this matrix always brings the variances, and that's expected because one way to think about the variance is the covariance between one feature and itself. If you actually do that in the formula of the covariance, you would reduce to the formula of the variance. And also, one thing that I want to mention is that the size of the covariance matrix would depend essentially on the number of features that you have. So if you have 2 features, you have a 2x2 covariance matrix. If you have 10 features, you would end up with a 10x10 covariance matrix. And this covariance matrix is always a square matrix. So these are a few examples of data that are generated by the same mean in the same covariance, but they are coming from the same specification of the way that we specify the probability distribution. But as you can see in each of those plots here, these are actually quite different in terms of how these points are distributed, are spread in the input space. So this is just to warn that it is actually possible that the mu and the covariance, or the mean and the covariance, is not enough to fully describe everything that you need to know about the data. But it's usually the beginning points that are used in most models to generate the to model the probability distributions that would be used on our Bayesian models. So now let's finally talk about the Gaussian. So the Gaussian, or the normal probability function, is also referred as the normal density function, and sometimes referred to as the bell curve function. These are just all different names for the same beast. So what you see here in this slide is the equation of the probability function of a Gaussian for a one-dimensional Gaussian, to be more precise. So the way that we usually refer to that probability function is by using this fancy n symbol here. And here we are essentially, because this is a probability distribution, right? So this is a probability that is a probability of the input of x, and is conditioned on the parameters that determines that curve. So that curve is, as I said, determined by these two parameters, the mean and the standard deviation, and or equivalently, if you square it to the variance. These would be applied to the case where you only have one single feature, because this applies to a single dimension, a single feature. This function, as any probability function, would obviously respect the constraints of any probability function, because this is a continuous function. So now we are talking about a probability density function. The difference between a probability density function and a mass function is that the density function cannot be taken as the actual prediction, the actual probability of a given input. Instead, it doesn't really make sense for us to do a point estimate, but we need to think in terms of areas that are covered by that curve to reach a specific estimate of a probability. So in other words, that's the same as saying that if you integrate that function that you see here, you would end up with some probability if you go from minus infinity to positive infinity. So as any probability functions, you would have that equals to 1. And also, as any probability functions, all the outputs that you would have would be greater than 0. So if we observe this function here, let's go over each term that we have here. In these dotted red box that you have here, you have 1 over 2 times pi. Pi is just the pi constant, times the standard deviation squared, and then the square root of that. That is multiplied by the exponent, so same as multiplying by the e constant, the e number, and to the power of minus 1 over 2 times, again, the standard deviation squared, times x, which is my actual input, minus the mu, which is the mean value of that feature, and then you square all that. So essentially, everything that you see here is being given by your conditions, your parameters here in your distribution. So the mu and the standard deviation are the parameters that we are using to parameterize that function. But there's also the x here, right? So what's the x? The x is just the input that you have. So if you plug in your mu and your sigma, your standard deviation, in this equation here, you would end up with an equation that only depends on x, only depends on your input. So now essentially you can provide that input and you would have the output of that function, of that normal probability function. All right, now let's generalize that idea of a Gaussian to the case where we have no longer only a single dimension, but now we have many dimensions, so 2 or more dimensions. In this case, as you can see here, the equation is actually quite similar to what we had before, but there are some differences, and let's go over those differences. First, the mu here, that is one of the parameters, is no longer a number or a scalar, but now we are talking about the mu, the mean vector, as the mu. And the sigma that you see here is the covariance matrix. So before, recall that we had the mean and the standard deviation. Now we have the mu, which is the mean vector, and the sigma, which is the covariance matrix. So again, let's go over these first term that we have here. So we have 1 over 2 pi to the power of d. D in this case is just the number of dimensions that you have. So for instance, if you have a 2-dimensional space, as what you have here in this example, d would be equals to 2. Sigma is our covariance matrix, and these bars here represent the determinant of the covariance matrix. So I take the determinant of the covariance matrix, that's a number, that's a scalar, and then I take the square root of that result. So that would be the second part of this term here. And then to the right, I would have, again, e to the power of all that. So this is kind of similar to what we had before. In this case, however, we have x as a vector, because recall that we have no longer one single feature, but many features. So then x now is actually carrying multiple values. So that's why we consider x to be a vector. Likewise, mu, as we mentioned before, is also a vector. So this is just subtracting x, which is my input, from my mu, my mean vector. This is transposed to make it compatible with the inverse of the covariance matrix. So you need to calculate the inverse of that covariance matrix. That's just the covariance matrix that we have used as a parameter for that Gaussian. And then you have essentially the same thing, but now you would consider that to be not transposed because you want that to be a column. So in this case here, in these equations, when you see a vector, most cases you would consider that to be a column vector. So that's what you see here. So a subtraction of two vectors that are column vectors would also result in a column vector. So essentially this part here would result, because we are transposing, would result in a row vector. The right-hand side here would result in a column vector. And the inverse is just a square matrix, same as the covariance matrix. So if you check one more time these diagram here, you see that now you have these topological curves, and these topological curves are essentially rings that are used to represent the points that have the same value as probability outputs, as probability as the output of that Gaussian. So all the points that sit on the same curve essentially are equally likely to occur according to that probability distribution. So this gives a good intuition on overall the shape or the likelihood of a given input, depending on where that input would be sitting. So the closer the input is to the center of this region here, the closer it is to the mean. So the center of all these curves are actually precisely the mean vector. And the closer it is to the mean, the more likely it would be, because the Gaussian has the apex precisely at the mean. So that essentially concludes. These are a few examples where we are using different covariance matrices to generate a few data points. So as we said, as soon as we have probability functions, you can use that probability function to generate data, right? So it's kind of the other way around. A lot of models would check the data from the data set and then make assumptions on the data, would essentially set up the model itself. When you are modeling using Bayesian modeling, what happens is that the probability functions can be used to generate the data itself, which is something quite interesting. All right, that is the end of the first part on Bayesian decision theory. I will stop the video now, and in the next video we will continue our discussion on the Bayesian models.